This is 6.2.1.3, page number 7. In this case, we are going to use direct inspection to analyze the complex exponential using DTFS. We know that this is the equation representing the signal. We also figure out that for DTFS, we need to find the fundamental period or the fundamental frequency that is going to be associated with the DTFS complex exponential. We know that it is 2 pi over big N. So the problem now is to find what is the N necessary to analyze this complex exponential. We have seen that when N equals to 10, then this would be the fundamental period. We should use that. So 2 pi over 10 is the correct value to use to analyze this complex exponential. In the inspection, what we are simply doing is we are actually comparing the synthesis equations with the original input signal, and then we will be able to identify CK. What am I talking about? Well, this is CK has been shown to be this equation. If you are writing your MATLAB code, then you are generating xn, and then you're also generating this complex exponential with different k's to calculate ck's. However, in the synthesis equation, we can directly find ck if xn is represented by this formulation anyway. So it looks very similar. Take a look at xn now. The amplitude is 3. The complex exponential minus 0.5 pi. So we know that this synthesis equation don't have phase shift. So what do? Well, we take this phase shift out, and then now we have 3 multiplied by ei minus 0.5 pi to represent the ck. So this thing is actually c something. Well, we do not know what is, but it looks like 3 e j minus 0.5 pi. Now, what about this signal? This signal is actually one of this signal. E, I, 2 pi over n, k, n. So the only difference is now what is the value of k and what is the value of n. Well, we have realized that we should find the capital N, the fundamental period, and substitute here. So omega naught, the fundamental frequency of the complex exponential, is 0.2 pi. So if we match 0.2 pi and here is 0.2 pi, then k would be set to 1. So we now identify that this is k is equals to 1, and the magnitude and phase is 3 for magnitude, and phase shift is minus 0.5 pi. So we can find by direct inspection C1 is equals to this value, which is what's apparent when we see this example anyway. This is C1 over here, has magnitude 3 and phase shift of minus 0.5 pi. The rest of the values are 0 because you will see that in this example there is no more other requirements of complex exponential at any other frequencies, because xn can be fully represented by this c1 over here multiplying by the corresponding complex exponential at omega naught. In the next slide, we'll see direct inspection by synthesis for a sinusoid. But here we have ended this slide. Thank you.